So in this short video, we're going to look at the sort of reaction benzene does. So remembering that the pi bond above and below the plane of the ring is an area of high electron density. Interestingly, it's not as high as in a double bond because it's delocalized, but it's higher than in a single bond because it is a pi bond. So there's more electron density than a regular single bond, but there's less electron density than a normal double bond. But it is high, and therefore it is going to attract electrophiles. Electrophiles being things that want to accept a pair of electrons. And because it's stable, it doesn't want to lose that stability by losing the delocalization. And so rather than doing addition, it's going to do substitution. So we're going to take our benzene ring, which remember we draw skeletally, and we're going to react it with some sort of electrophile. So say we have this thing X2, that might be Cl2, there might be a catalyst involved. We're going to swap one of the hydrogens that's invisible in our skeletal formula for the X, and we'll be left with HX. We've substituted H for X. Remember that we can do mechanisms using curly arrows, and curly arrows show movement of a pair of electrons. And they must start from either a lone pair or a covalent bond. I can't stress that enough to you, which is why we keep repeating it. You must start your curly arrow from either a lone pair or a covalent bond. So here is my benzene ring, and this is how the mechanism is going to go. Remember that pi bond, that circle in the middle, is an area of high electron density. And here's my electrophile. Now, if the exam board wants me to put the electrophile in a particular position, I'm going to have to pay attention to that, and I'm going to have to aim for that position. So imagine I'm trying to aim for this position here. See this one here? That one there? I'm aiming for that position there. So I want to use my curly arrow in roughly that area of the ring. And so what I'm going to do is, remember that a curly arrow starts from a lone pair or a bond. In this case, it's going to start from the pi bond. Just like in alkenes, it starts from the pi bond. So it's going to start from the ring. It's going to go out where I want to put that substituent, and it's going to grab onto it. It's going to get that electrophile. What happens then? Let's have a think about it. It's gone and grabbed it, and it's put it there. And there was already a hydrogen there, and I haven't done anything about that hydrogen yet, so I'm going to draw that out. What has happened to the pi bond? So let's have a little think about what has happened to that pi bond. So what we had, that pi bond, we had 6 electrons in p orbitals delocalized over 6 atoms, spread out over 6 atoms. And when we drew that curly arrow, we moved a pair. We moved 2 electrons out of the pi bond and into this covalent bond here. So we moved 2 electrons out of the pi bond and into the covalent bond to the electrophile. And so the p orbital that was involved in the pi bonding on the carbon here is now involved in bonding to the electrophile. And so now there is still delocalized electrons, but they're not spread out over all 6 atoms. They're spread out over 5 atoms. But how many electrons are spread out over those 5 atoms? We had 6, and we moved a pair, so there's now 4 electrons spread out over 5 atoms. How are we going to show that in our mechanism? Well, we've broken that pi ring, but it's still spread out over 5 atoms. So let's go back to our mechanism and have a look. So we've broken that pi ring, but what we've got left is still spread out over 5 atoms. Now, be careful, the 5 atoms go from here to here. Yes, I'm going to remove that line in a minute, but we do need to think about that line. So those 5 atoms are going from there to there. Right. We're going to have a pi bond now that goes from there round to there. Now we need to not have that line in our mechanism, so we do need to remove that. So we just get rid of that line. And we do have the electrons spread out round those 5 atoms. So make sure your horseshoe, the exam board will often refer to that as a horseshoe, opens towards where you've put the electrophile, but extends only around those 5 atoms. And then, because you've given away electrons, that's become positive. Then what happens? Well, then the substitution occurs. So something has to fall off. So this hydrogen is going to fall off. The curly arrow is going to move the pair of electrons back to reform the pi bond, because remember that's giving us lots of stability. And so we've got the electrophile, we've reformed the pi bond, and the hydrogen has fallen off as a H plus ion, hydrogen ion. And that's the basis of our mechanism. 2 curly arrows. That horseshoe shape in the middle is probably the most important factor to get right. So benzene will undergo this substitution rather than an addition like other things with pi bonds. It doesn't want to do addition, it wants to do substitution, because that is going to preserve the stability of the delocalized pi ring. Remember, delocalization gives stability. So it's going to preserve the stability of the delocalized pi bond. So we're going to take each one of these mechanisms in turn now.